Let's look at the orthogonal complement of a set of vectors. Let S be a set of vectors in Rn. The orthogonal complement of S, which we denote by this symbol, we say S perpendicular or S perp, kind of a strange term, is the set of all vectors in Rn that are orthogonal to every vector in S. So let S equal the single vector V. What is S perp? All the vectors perpendicular to V. For example, let V be the two-dimensional vector 3, 4. Geometrically, what is S perp? Well, here's 3, 4. One vector that's perpendicular to 3, 4 is this red vector 4, negative 3. In fact, if you look at all the vectors that are perpendicular to 3, 4, they're all going to be parallel to 4, negative 3. So, in fact, S perp consists of all multiples of 4, negative 3. Let S equal the single vector V, where V is a three-dimensional vector. What is S perp? Again, it's all the vectors perpendicular to V. But more precisely, let V be the three-dimensional vector 1, 2, 3. Geometrically, what is S perp? S perp, again, is all the vectors perpendicular to V equals 1, 2, 3. In other words, S perp consists of all the vectors in any plane perpendicular to 1, 2, 3. Here's why. We have this vector 1, 2, 3. It's this black vector here. What we want is the set of all vectors that are perpendicular to this vector. Well, if you look at the set of all vectors that are perpendicular to this vector, they're going to form a plane that's perpendicular to this vector. It's going to look something like this. In fact, if you look at any plane that's perpendicular to this blue vector 1, 2, 3, the vectors in that plane are going to be perpendicular to 1, 2, 3. And you can see this. We can take different shots, look at different angles. Ooh, there's a nice side angle. You can see how well that plane is perpendicular to that vector. Let S equal V1, V2, where V1 and V2 are three-dimensional vectors that are not parallel. What is S perp? Again, it's all the vectors perpendicular to both V1 and V2. For example, let V1 equal this blue vector, 1, 2, 3, and V2 equal this green vector, 1, negative 1, 1. Geometrically, what is S perp? S perp is all the vectors perpendicular to both V1 and V2. What's that going to look like? Well, the vector 5, 2, negative 3, for example, is perpendicular to both V1 and V2 because the dot product of 1, 2, 3 and 5, 2, negative 3 is 0, and the dot product of 1, negative 1, 1 and 5, 2, negative 3 is 0. So 5, 2, negative 3 is in S perp. How did I get 5, 2, negative 3? Well, in Calculus 3, we learned that V1 cross V2 is 5, 2, negative 3. And V1 cross V2 produces a vector that's perpendicular to both V1 and V2. Now, if you look at this illustration, I can believe, it's kind of hard to believe that this red vector is perpendicular to those others. It doesn't really look that way. We'll see in a moment why that's the case. If you look at it from a different angle, now it seems more plausible that the blue vector and the red vector are perpendicular. And if you look at it from this angle, now it seems more plausible that the green vector and the red vector are perpendicular. Pardon me. It turns out that every vector in S perp is a multiple of 5, 2, negative 3. Let A be an m by n matrix. Find row A perp and column A perp. In other words, find the row space of A perp and the column space of A perp. It turns out the row space of A perp is the null space of A, and the column space of A perp is the null space of A transpose. Why is that? Let's say A is a matrix that looks like this. I haven't filled it with numbers because you would get lost in the details, and I don't want you to do that. So suppose X is in the null space of A. We're going to show that X is also in the row space of A perp. The null space of A, recall, is the set of all vectors X such that X1, X2, X3, X4. It's the set of all vectors X, X1, X2, X3, X4, such that AX equals 0. In other words, we've got something that looks like this. So this is our A, this is our X, and that's 0. Notice what this implies. The dot product of row 1 and X is going to be 0. And the dot product of row 2 and X is going to be 0. The dot product of row 3 and x is going to be 0, and the dot product of row 4 and x is going to be 0. The vector x is orthogonal to each row in A. So x is orthogonal to any linear combination of the rows in A. You can show that algebraically. Therefore, x is in the row space of A perp because everything in the row space of A is a linear combination of the rows of A. And we just saw a moment ago that any linear combination of the rows of A is going to be perpendicular or orthogonal to x. Okay, so we just showed that if x is in the null space of A, then x is in the row space of A perp. Similarly, we can show that if x is in the row space of A perp, then x is in the null space of A. So notice this. X is in null space of A implies that x is in row space of A perp. X is in row space of A perp implies that x is in the null space of A. Therefore, these two sets are the same. The row space of A perp is the null space of A. Also, the column space of A perp equals the null space of A transpose because the columns of A are just the rows of A transpose. So we can just apply the result we just proved. The column space of A perp, that's the same thing as the row space of A transpose, perp. And by this result that we just showed, the row space of A transpose perp is the null space of A transpose.